I'm really happy to meet you again. And this is another theorem. It's a very important theorem. They may ask in the university examination. A k minus 1 regular bipartite graph is one factorable. You know what is a regular bipartite? Am I correct? That is, every edge has k minus 1 degree. That's what bipartite graph. Every vertex has k minus 1 degree. That's called regular bipartite graph. Bipartite, we know that the total vertex can be divided into two sets, as you see in the picture. You see the nearby picture is two sets shown on the blue color, and that's what x and y are two sets where the two vertices v1, v2 is in one set and v4, v3 in the other set. So bipartite graph. Now we say that is one factorable. One factorable means what? One factorable means the degree of the vertex is only 1. That's called one factorable. Degree of 1 become one factorable. And also they are disjoint edges. That we will look at now. If E of G be the edge set of G, which implies K of X is less than or equal to E of G is less than or equal to K of Y. You know what is K here? The number of vertex is called K. Here number of edges, that's called E. Now we have to prove this, okay? Right. Now where x comma y is bipartite, so we are taking an edge set of G in this particular graph. It consists of v1, v2, v3, v4, all the edges, and such that the vertex in x is less than or equal to the length of the vertex G less than or equal to the length of the vertex y, where x comma y is a bipartite. That's what we have to understand, bipartite. Now let S is a subset of X. If S is a subset of X, definitely N of S, the neighborhood of images of S, would be contained in Y. Neighborhood of images of S would be contained in Y. That is what implies. So let E1, E2 be the set of edges incident to S. So incident to S, E1 and E2 be the set of edges incident to S and S respectively. Since the E2 is greater than or equal to E1, okay, E2 is greater than or equal to E1. Why? Because yes, we are taking as E1 and the N of S, the neighborhood of S, that vertex we are taking as E2. Therefore, the length of the E2 is always greater than or equal to the length of E1. Definitely, there is no doubt at all. Am I correct? Because we have chosen E1 and E2 such that N of S containing Y. Therefore, we have the absolute value of E2 is greater than or equal to absolute value of E1, which implies the absolute value of N of S is greater than or equal to absolute value of S. Okay, because we have assumed so. By theorem, G has saturated matching. So from the previous theorem, see there, if this is the case, then G has a saturated. You go back, you will see that. That's the theorem here. This is what the previous theorem we saw that. Am I correct? If it is a bipartite graph, bipartization x comma y, then absolute value of N of S is greater than or equal to absolute value of S. Then G has a matching, which is a saturated one. So by that particular theorem, we proved that k minus 1 regular bipartite graph is one factorable. Look at this picture there. X, Y are two bipartization, V1, V2 are the S, and Y is N of S here, okay, neighborhood of S vertices. Now I repeat I replace one edges here, it becomes k minus 1 regular bipartite graph. Now look at the picture down. If it goes away, then you replace this V4, V3 edge away, then you will have the one factorable. It is a picture disjoint edges having one factorable, because each vertex has only 1 degree. Therefore, it is what? One factorable. Okay. Therefore, if k minus 1, a regular bipartite graph, if one edge is thrown it away, we can make this down picture, that this also if you take away, you can have V1, V4, 1 and V2, V3 other two are independent of one another, and thus it is one factorable because the degree of each vertex is 1. Okay, that is what we have to understand. This theorem is a very important theorem. This is what the next theorem. Okay, the theorem says that in a bipartite graph, the minimum number of vertices that cover all the edges of G is equal to the maximum number of independent edges. Bipartite graph, we know that. Okay, and minimum number of vertices means minimum number of independent vertices that cover all the edges of G is exactly equal to the maximum number of independent edges. There is a connection between minimum number of vertices and the maximum number of independent edges. Minimum number of vertices means minimum number of independent vertices. That is left out here, and that equals the maximum number of independent edges. That's what we have to prove here. Now let us prove that. Right, now it is a bipartite graph, so I am dividing the whole graph by two sets, x and y, such that x consists of one vertices set of vertices and y consists of another set of vertices. Okay, such that the each edges, the initial edges is in the first set and the final edges on in the second set. Okay, now I am taking one vertex which is unsaturated by M. Unsaturated by M, that is that vertex is not covered by this matching. Okay, so like that I am assuming this particular picture. Now there are two covering exist here. One is the neighborhood of S, where S is the subset of the graph, and that I am taking as T. Okay, and definitely K equals T union X subtract S. Y means what? K means what? Total number of vertex. That must be equal to T, then the neighborhood of the vertex is S, and subtract S from the capital X. The first is at capital X. This is true. K equals T union X subtract S. But first one is contradiction. First one is means what? N of S is a contradiction. Why contradiction? Now look at this, the picture. T is equal to Y intersection Z. So the vertex is unsaturated M. Therefore, the one vertex left out there. So we cannot say that neighborhood of S is equal to T. So first factor is contradiction exists because of the edge on S cannot have incident at T. So the possibility is K must be equal to T union X slash S. Of course, this must be equal to M, the matching. Okay, because one element is left out, therefore this gives us the matching. Okay, therefore the absolute value of K, the number K we know that is a number of vertices. So number of vertices will be equal to T union X slash S, that equals the number of independent edges. So the number of independent vertex equals the number of matching, or we can say number of vertices equals the number of matching. Okay, that means the length of K, that is number of vertices, minimum number of vertices, would be equal to M. the maximum number of independent edges. Okay, that is the number of independent vertex equals the total number of independent edges. That's what we see here. Or we can say that minimum number of vertex equals the maximum covering, the maximum independent covering. That's what we proved here. So this is a way we can prove this particular theorem. Okay, so this theorem also very important theorem, and thus we prove that in a bipartite graph, this is possible only in bipartite graph. The total minimum number of independent vertex equals the maximum number of independent edges. Okay, so this theorem is also very important, this theorem also very important, and this theorem also very important. So very important theorems are there. So with that, I have to come to the end of this program, and I will be looking you in another program. Okay, with that I come to the end of this particular program. Thank you very much, friends. Thank you.